Hi, so today we're going to deal with limits involving infinity. This topic is actually relatively small, but it's really important to what we're going to do in calculus, and it actually kind of throws back to something that we talked to you guys a little bit in pre-cal regarding horizontal asymptotes. So back in pre-cal when we were first looking at horizontal asymptotes and we were looking at rational functions, we were looking at the degree of the denominator versus the degree of the numerator, and we basically just threw out there and told you, look, if the degree of the numerator is greater than the degree of the denominator, then there's not going to be a horizontal asymptote. And if the degree of the numerator is less than the degree of the denominator, then y equals 0 is the horizontal asymptote. And if they're equal to each other, if the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is the leading coefficient of the numerator divided by the leading coefficient of the denominator. And that worked great in pre-cal, but we kind of had to throw that out there to you and just kind of tell you that's the way it was without really explaining to you why that is. So now that we've got an idea of what we mean when we're talking about a limit, we can look at what actually happens with these horizontal asymptotes and why they are what they are. So we're going to look at a couple of functions today, and we're going to look at why the horizontal asymptote follows these guidelines that we're looking at here. So the first equation that we're going to look at is going to be, let's do the limit as x tends to infinity of x squared minus 3x plus 2 divided by x plus 6. Now, according to our pre-cal rules, this shouldn't have a horizontal asymptote at all. And what that means is, as x goes to infinity, the y value, or f of x, is going to increase without bound as well. So that means that since we're looking at the limit now, as x goes to infinity, this should have no limit. It shouldn't be approaching any particular value at all. Now, there's not any way to simplify this function algebraically, so we can't calculate this the way that we were looking at in the last video. But there are some things that we can do. And the way that we're going to handle this is we're going to first of all identify what the largest degree in this whole rational function is, in the numerator and the denominator. And in this case, the largest degree is 2. So what I'm going to do is I'm going to divide every term in this function by that term right there, by the x squared. And when I do that, I'm going to get the limit as x tends to infinity of x squared over x squared minus 3x over x squared plus 2 over x squared divided by x over x squared plus 6 over x squared. And now, while it seems like I complicated the function, and it looks like I really did complicate the function here, but now when I apply the limit, it's actually going to tell me something. So I think before I do the plugging in, evaluating this, so I think I'm going to simplify these at least as much as I can, because there are some things that will cancel out here. So let's take a look at what happens when we do some reduction on these terms here. X squared divided by x squared, that's going to be equal to 1. And in the second term, x will cancel one of these x's down here, leaving me with 3 over x. Nothing I can do with the next term, so it's going to stay 2 over x squared. Here, this x cancels one of those, leaving me with 1 over x, plus, and nothing I can do with this last one. Now, if I look at what happens when x approaches infinity, remember your rule that says that if you divide by something big, then the result is something small. If you divide by something small, the result is something big. Well, it turns out that in all of these cases, this one, this one, this one, this one, all of these are getting incredibly small. So this is getting small, this is getting small, this is getting small, this is getting small. And so I end up with basically 1, because I've got 1 plus or minus something very, very small, divided by something very, very small. Now, whatever that value is, it's not 0, because I'm not letting this go to infinity, or I'm letting it go to infinity, but it's not equal to infinity because it's not a number. Basically what that's doing is it's making these numbers get smaller and smaller and smaller, which makes the denominator become very, very small, and when I divide by something very, very small, the result is something very, very large. So this is going to be going to infinity. So, like we expected, as x increases without bound, the function will increase without bound as well. Exactly what we told you in pre-cal was going to happen. Okay? Now, let's take a look at maybe something with a little bit different situation. And I think with this one, we'll just, tell you what, let's just switch the numerator and denominator here. And this time we'll look at x plus 6 divided by x squared minus 3x plus 2. So very similar function, we've just taken the reciprocal of it, but this time the degree of the numerator is smaller than the degree of the denominator, and according to our pre-cal rules, that means that the horizontal asymptote should be approaching 0. In other words, the limit as x tends to infinity should be getting closer and closer to 0. It should be leveling out at 0. So let's see if that's really what happens. I'm going to do the same thing I did a second ago. I'm going to identify the largest term in the polynomial. In this case, it's the x squared. I'm going to divide by everything in that term. So if I take the limit as x tends to infinity of x over x squared plus 6 over x squared divided by x squared over x squared minus 3x over x squared plus 2 over x squared. And again, I'm going to simplify this function as much as I can. So I'll have the limit as x tends to infinity of, let's see, x over x squared is going to give me 1 over x plus 6 over x squared divided by 1 minus 3 over x plus 2 over x squared. And now, as I look as x tends to infinity, this term and this term are going to get closer and closer to 0. This term and this term are going to get closer and closer to 0, which means that denominator is going to get closer and closer to 1. And I end up with 0 over 1 or 0, exactly what we thought was going to happen. As x increases without bound or tends to infinity, the function is going to get closer and closer to 0. Okay? Now, let's verify that last situation where the degree of the numerator and the degree of the denominator are equal to each other. So let's take the function 3x squared plus 4x minus 1 divided by 2x squared plus 6x plus 3. Okay? And I'm going to look at this as x increases without bound, or as x tends to infinity. Same situation I had a second ago. I'm going to divide everything by the highest power degree. In this case, the highest power degree shows up in 2 places. Not a problem. I'm going to divide everything by x squared. So I'm going to get the limit as x tends to infinity of 3x squared divided by x squared plus 4x over x squared minus 1 over x squared divided by 2x squared over x squared plus 6x over x squared plus 3 over x squared. And again, I'm going to reduce this as much as I can. That's going to get me the limit as x tends to infinity of 3 plus 4 over x minus 1 over x squared divided by 2 plus 6 over x plus 3 over x squared. And now when I look at this as x increases without bound, this term, this term, this term, and this term are all going to go closer and closer to 0. So I'll end up with essentially 3 plus nothing minus nothing, which is 3, over 2 plus nothing, or 2. And so I end up with the leading coefficients of the original function, 3/2. There's my horizontal asymptote. So you can see that what we told you in pre-calculus about why these horizontal asymptotes do what they do as far as the degree of the polynomials has everything to do with limits. And this is how we're going to handle these limits as we're working through them. We're going to look and see, okay, simplify the function as much as we can, and then determine what happens to the function as x tends to infinity. Now, there's some other situations that we've got going on with limits involving infinity as well, and they deal with vertical asymptote. So let's take a look at a couple of those situations. Let's say that we have the function, the limit as x approaches 2 of 1 over x minus 2. Now, this one is a little bit more difficult because we have to kind of pay attention to what's happening to the left and the right of 2, because we're not looking at what's happening as x tends to infinity, we're looking at what's happening as x tends to a particular value. So we have to look at it from both sides. So there's no real algebraic simplification for this. There's not much that I can do, but I'm going to kind of think my way through this and see if I can figure out how this is going to behave. So let's look at it first of all from the left-hand side. Okay, if I look at the limit as x tends to 2 from the left-hand side, that means x is becoming something like 1.9, 1.99, 1.999. Okay? And if I start thinking about what happens if I plug those values in for x, then what I would get is essentially, and you can plug this in with your calculator and actually calculate these things, but you would get 1 over 1.9 minus 2, or 1 over 1.99 minus 2. And you can kind of see that this is going, okay, that's going to be 1 over negative 0.1. This is going to be 1 over negative 0.01. And as we extend that out, the denominator would get larger and larger and larger in the negative direction, smaller and smaller and smaller in the negative direction, which makes the entire function become larger in the negative direction because I'm dividing by something small, so the result would be something big. So from the left-hand side, this is going to become very, very large, and it's going to be negative. So this is going to approach negative infinity from the left-hand side. Now, if I look at this from the right-hand side, it looks pretty much the same way. We'll take the limit as x tends to infinity, extends to 2 from the right-hand side. That's going to give me something like, let's see, if from the right-hand side, I'm going to be doing 2.1 and 2.01 and 2.001. So that's going to give me 2.01 minus 2, which is going to be 1 over 0.1, or, well, 0.01 for that one. And then maybe we're doing 1 over 2.1 minus 2. So you can kind of see that, again, as x gets closer and closer to 2, then the denominator becomes very, very small. The result is very, very big, but this time the result is positive. So from the right-hand side, if I look at the limit as x approaches 2 from the right-hand side of the function, it would go to positive infinity. Now, if you look at the graph of this, it kind of makes sense because the graph of this from the left-hand side goes down like this, and from the right-hand side it comes up like this, and you have this vertical asymptote at x equals 2. So it's exactly what we thought it would do if we were to just look at the graph of it. Not really any algebraic way to explain this other than just kind of go through and try and plug in points and try and determine what's happening there. And you can kind of see our denominator's getting smaller and smaller and smaller, and so our result of the whole thing is getting larger and larger and larger. Okay, so that's kind of what's going on with these things. Let's take a look at another one, something similar. Let's look at the limit as x tends to 2 of x minus 2 squared. Okay, so a very similar function, but let's do x minus 2 quantity squared. Okay, and again, you'd have to look at this from both the left and the right-hand side. And let's not worry about writing everything down. Let's just kind of think about this mentally and see if we can figure out what's going on here. When x is approaching from the left, I get 1.9, 1.99, so forth. That's going to make this negative something very small, like 0.1 or 0.01. And then I'm going to square it. That's going to make it positive again, but it's going to make it even smaller. Okay? So when I do that, I'm going to end up with something that is 1 over something small and then squared. And because it's squared,
Doesn't matter if this turns out to be positive or negative, so it doesn't really matter if I'm coming from the left or the right. The result in the denominator is going to be positive. I'm always going to be dividing by something small, and so the result will be something very large, and so that's tending to infinity. Okay, so that's the way to handle these vertical asymptotes. A lot of times there's not a way to simplify these things algebraically. You really have to kind of reason through, okay, if x is approaching this value, what's actually happening to the function? So these are a little bit more difficult to deal with, but it really is just an extension of what we're talking about with the other limits, trying to get the x value to be closer and closer to a particular value, and then seeing what happens with the function. In this case, the functions are going to infinity or negative infinity. Thanks.